section 1.0 of the live code notebook. We work on modeling uniformly randomly distributed vectors in 3D space. Later we do 2D. And basically at this point in time, all we want to do is just change the direction of a vector at a particular pivot point. And we do that by this very simple code here that we have developed in Wolfram Mathematica. Put your mouse any place, click on any lines in this area called the expression cell, and then do a shift enter. When you do a shift enter, the bluish variables disappear, become black. That means when they were blue, were unassigned or undefined. Now they are black, that means they have value. And the ones with the square bracket like these are functions which they make us the vectors. And this is where the pivot point R0 is, and depending on the dimension will be 2 zeros or 3 zeros. Once we do that, then let us go and apply a little bit more code and see if our function over here, a function of time, can actually give us random vectors. And put on this cell over here, the expression cell corresponding to this one line statement, put your mouse any place and make a click, and then press shift down and enter. There you are, and you can make indefinitely many random coordinates here. Notice that when we have this thing called d, which is the length of the vector, and I gave it an odd number so it's recognizable later on. If you create a random vector here in this cell, go in this additional cell here, and you basically measure its length, Euclidean geometry, you notice that the length is precisely what you had in the variable d. And if you generate another vector, although it's random, you compute the length is exactly that weird number. And then finally we come down here and plot it. Let me see if I can go here. Oh, very good. We can actually plot it. And if I generate the vector again, come down here and plot it again, you can see each time I'm getting a different vector. Okay. So now what we're going to do next is we are going to iterate that process by using Wolfram Mathematica the function called table, and in this case I'm adding iteration of 2. Go to this any place, you type the code here, left click your mouse and then do shift enter, and it gives you two random vectors. If you increase that to 3, magically it will give you 3 randomized vectors, as you can see. 1, 2, and 3. I warn everyone, I'm getting giddy, sorry. And then we want to do a larger one, so we're going to put 100 over here, and we run the code. Same thing, click any place, shift enter. And there's a useful command in Mathematica, use just short, which any large structure, it will give you a bit of the beginning and a bit of the end. Here you are, and you can see it remains the same. Run the f list again, this variable f list equal to table. Run that again, you get pretty much different number. Run it again, you get pretty much, because the vectors are always random. Now we're gonna do the wild thing of actually plotting that in 3D, pivoted at point R0, which was 0, 0, 0, if you remember. And look at what happens. Magic happens. You have now shown that those funky random code that you wrote, they're actually a beautiful dandelion looking creature that you can see here. And yeah, you can play with it, make it bigger and smaller and all that, beyond the subject matter of this discussion. Now, in order for us to convince you that these are actually all the same length, we do the next wild thing is that we plot it and then we plot the semi-transparent, that means the opacity comment here, and we do a sphere of that length d that we discussed before, and let's see what happens. Ooh, look at this. You can see that the endpoint of every single vector is on the circumference of the sphere. That means it has the length d. And this is how we model the distribution of the impulse force applied to that one particular ball that contains an atom or contains a molecule.